The long spark, a human story of electricity. Long before electricity had a name, it had a feeling. Somewhere in ancient Greece, around 600 BCE, a philosopher named Thales of Miletus sat with a piece of amber in his hand. Amber was beautiful, fossilized sunlight, but Thales noticed something strange. When he rubbed it with fur, it began to pull light objects, feathers, dust, bits of straw, toward itself. There was no flash, no sound, only motion without touch. Thales could not explain it, but he had witnessed a force. The Greeks called amber electron. From that word, centuries later, electricity would take its name. For nearly 2,000 years, electricity remained a curiosity rather than a tool. It appeared in nature as lightning, terrifying, divine, uncontrollable. Humans watched storms from caves and temples, believing the sky was alive with gods. The spark was there, but humanity had not yet learned how to hold it. Sparks in the dark, early experiments. By the 1600s, curiosity had become method. In England, William Gilbert, physician to Queen Elizabeth I, began experimenting with magnets and static attraction. Unlike Thales, Gilbert did not merely observe. He tested. He rubbed glass, sulfur, and resin, discovering that many materials could produce attraction, not just amber. In 1600, he published De Magnete, introducing the idea that electricity was a natural phenomenon governed by laws rather than magic. Electricity stepped out of myth and into science. Still, it was weak, static, fleeting. A spark that vanished as soon as it appeared. Then, in 1745, in a small laboratory in the Netherlands, Peter van Musschenbroek accidentally trapped electricity inside a glass jar filled with water and metal. The Leyden jar was born, the first capacitor. Electricity could now be stored, released, and measured. For the first time, humans could save lightning. People shocked themselves for entertainment. Scientists lined up volunteers to feel the jolt. Electricity was still a novelty, but now it had teeth. Taming lightning. Franklin and the sky. In 1752, in Philadelphia, Benjamin Franklin stood beneath a storm cloud. With a silk kite, a hemp string, and a metal key, Franklin tested a radical idea, that lightning was the same force humans produced in laboratories. When the key sparked, Franklin confirmed it. The heavens and the earth were connected by the same electrical law. Franklin did not invent electricity, but he gave it language, positive and negative charge. More importantly, he made it practical. His lightning rod transformed electricity from a destroyer into a protector, saving buildings and lives. Electricity was no longer only feared, it was useful. Motion into power. Galvani and Volta. In the late 1700s, electricity entered the body. In Italy, Luigi Galvani observed a dead frog's leg twitch when touched by metal. He believed he had discovered animal electricity, a vital force inside living creatures. But another Italian scientist, Alessandro Volta, disagreed. Through experimentation, Volta showed that the electricity came not from life, but from the contact between different metals. In 1800, Volta stacked discs of zinc and copper separated by brine-soaked cloth. The result was the voltaic pile, the first battery. For the first time in history, electricity flowed continuously, on demand. Electricity was no longer a momentary spark. It was a current. Invisible rivers, Faraday and Maxwell. In the 1800s, electricity became a system. Michael Faraday, once a bookbinder's apprentice, discovered that moving magnets could generate electric current. His experiments revealed electromagnetic induction, the principle behind electric generators and motors. Faraday showed that electricity and magnetism were not separate forces. They were two faces of the same phenomenon. Later, James Clerk Maxwell transformed Faraday's experiments into mathematics. Maxwell's equations proved that electricity, magnetism, and light were all part of a single electromagnetic field. Light itself was electricity in motion. At this moment, electricity became predictable, and what is predictable can be engineered. Power for the world, Edison, Tesla, and the grid. By the late 1800s, electricity was ready to leave the laboratory. Thomas Edison focused on practicality. He improved the incandescent light bulb and built the first direct current power stations. Streets lit up. Night became optional, but electricity still struggled to travel long distances until Nikola Tesla envisioned a different approach, alternating current AC. With AC, electricity could be transmitted across vast distances with minimal loss. Tesla's system, championed by George Westinghouse, won the war of currents. Electricity became infrastructure. Cities glowed, factories hummed. Time itself bent to electric clocks. The modern pulse, from wires to waves. In the 20th and 21st centuries, electricity became invisible again, but everywhere. Electrons raced through silicon in microchips. Electricity carried voices through wires, then through the air as radio waves. Computers turned electricity into thought-like logic. The internet transformed it into connection. What began as a curious attraction between amber and straw now powers hospitals, satellites, and entire civilizations. Electricity is no longer something we notice. It is something we assume. Yet every time a screen lights up, every time a motor spins, it echoes that first human moment of wonder. Why did this move when I touched it? The spark is older than us, but the story of electricity is ultimately the story of human curiosity, of asking questions, risking storms, and refusing to accept mystery as the final answer.